Hello viewers, welcome to Ado. In this question, we are asked to explain the transistor biasing modes with circuit diagram for NPN transistor. Okay, so let us start with the question. So, we are asked about the biasing mode of a transistor. But the first question arises, why do we need to use biasing? So, we can see this transistor, the main application of the transistor is an amplifier, okay, which performs the amplification process. But the thing is, even when we are operating the transistor in an active region or in the C mode of operation, the transistor will changes its amplification factor based on the surrounding environment. Like, for example, T is equal to, for temperature which is equal to 25 degrees centigrade, we are getting an amplification factor of, suppose we are getting an amplification factor of 50. Okay. And now when this temperature is reduced from 25 to 15 degrees centigrade, this amplification factor will reduce from 50 to 30. Okay. So even when we are operating the transistor in an active region and we are using the C mode of configuration, due to different environmental condition, we are getting a different value of voltage gain or amplification factor. And this is a problem for us. So we need to make sure that even the temperature is changing. Suppose here in this case, it is changing from 25 degrees centigrade to 15 degrees centigrade. We need to make sure that the voltage gain of the amplifier remains the same or the amplification factor remains the same. So that is the main reason we use biasing. And the BJT biasing circuit are basically of three types. One is fixed bias, another is collected to base bias, another is voltage divider bias. Okay. So this is the three type of biasing techniques that we are using. And we will be selecting a particular biasing technique to bias our transistor based on its stability factor. So this stability factor, which is S, this is equals to 1 plus beta divided by 1 minus beta del of IB divided by del of IC, where IB is the base current and IC is the collector current. Okay. So we need to look out for this stability factor, right? So for each of these transistor biasing, we will find out the stability factor. Now, the value of the stability factor, it will have a minimum value of 1 and a maximum value of 1 plus beta. Okay. So if the stability factor is at its minimum value, which is 1, the stability will be maximum. Okay. So that amplifier will be much more stable than all the remaining biasing amplifier. And if the stability factor is maximum, then the amplifier will be least stable. Okay. So this is one of the principle that we will be using. So let us start for fixed bias. Okay. So at first we will draw the circuit diagram and then we will find out its stability factor to determine whether it is stable or not. Okay. So this is a transistor, this is the base, this is the collector, and this is the emitter. Okay. So here we are adding a collector resistance, and this collector resistance is feedback to a base resistance which is connected to the base here. This is RB, this is RC. The current which is flowing through it is IC, and the current which is flowing through is IB. Okay. And this is the base emitter voltage plus minus VBE. And this is the collector emitter voltage which is plus minus V of CE. Okay. So if we apply KVL, okay, if we apply KVL along this particular direction, if we apply KVL, one thing that we need to know that here we will be having our supply voltage, which is VCC. Okay. So if we apply KVL along this side, we will be getting VCC is equals to, this is IB and the current which is the resistor is RB. So IB into RB, VCC is equals to IB into RB plus the voltage here at this point is V of BE and it can be also be written as V of B only. Okay. So this V of B or the base voltage is equals to VCC minus IB into RB. Okay. So if we decrease the value of RB, the value of VB will increase. Okay. As this is in minus. So if we decrease the value of RB, the value of base voltage will increase. Okay. And from this, we will have to find the value of IB, because here we can see the stability factor. This is del of IB by del of IC. So here we can find IB as IB is equal to VB minus VCC divided by RB. VCC minus VB divided by RB. If we take IB on this side, we will be getting VCC minus VB divided by RB. Okay. So this is the value of IB. And if we differentiate it with respect to IC, we will be getting what? We will be getting only 0. So if we put this value here, we will be getting stability factor is equals to 1 plus beta divided by 1 minus beta into 0. So this is equals to 1 plus beta. So as I have said, the maximum value of the stability factor is 1 plus beta. And if the stability factor is at its maximum value, then this will be least stable. So the fixed bias is least stable bias. Okay. So if we apply fixed bias, then the biasing will be least stable. Okay. So next up, we will move up to the collected to base bias. So in the collected to base bias, at first let us draw the circuit diagram for collected to base bias. So collected to base means this is the collected terminal. This is connected to base. Okay. So this is the collector resistance RC. This is the current flowing to the collector, which is IC. This is connected to a supply voltage VCC. This is RB. The current which is flowing through is IB. And this is the base voltage VB. And this is the base emitter voltage VBE. And this is the collector emitter voltage V of CE. Okay. So if we apply KVL in this direction, we will be getting IE is equals to VCC minus VC divided by RC. Okay. So we can see this VCC, this is the supply voltage here, and this VC, this is the voltage at the collected terminal. So at this point, the voltage is VC. So if we want to find the voltage drop between these two terminals, it is equals to VCC minus VC divided by RC. So this is the current which is flowing through the collector terminal. And as the collector current is almost equals to emitter current, so we are using here emitter current is equals to VCC minus VC by RC. And one thing, previously I said we will apply the KVL in this direction. So if we apply the KVL in this particular direction, then VCC is equals to I into RC plus IB into RB plus V of BE. Okay. So VCC is equals to, here we have taken IE instead of IC because they are almost equal. So IE into RC plus IB into RB plus V of BE. Okay. Or we can also say just V of B. Okay. So from here, we will find, as we know, this emitter current is equals to base current plus collector current. So this VCC is equals to IC plus IB into RC plus IB into RB plus V of BE. Okay. So from here, we will find the value of IB, and the value of IB will be equal to VCC minus IC RC minus V of BE divided by RC plus RB. Okay. So if you just multiply all this and take the value of IB common from the equation, we will be getting this equation. Okay. So this del of IB divided by del of IC will give us minus of RC divided by RC plus RB. And we will just put this value in this equation. So for this case, the stability factor is equals to 1 plus beta divided by 1 plus beta into RC divided by RC plus RB. Okay. So this is the stability factor for collected to base bias. And next we will discuss about voltage divider bias. Okay, so let's start with voltage divider bias. So at first let us draw the circuit diagram of it. So in voltage divider bias, the circuit diagram looks like this. Okay. This is connected to ground. This is connected to ground. This is R1, one resistance. This is R2, another resistance. Here this is the phase voltage V of B. This is the supply voltage. This is collector resistance. This is collector current IC. This is the collector terminal voltage V of C. This is the emitter current IE, and this is the emitter resistance RE. Okay. So here we will apply the Thevenin theorem to find the Thevenin equivalent circuit of this. Okay. So we are replacing R1 and R2, the parallel combination of it, as R of B, which is the base resistance. So RB is equals to R1 parallel R2. Okay. So here we are defining a Thevenin voltage. Then we are getting the R of B. Then we are getting the transistor. Then here at this point, we will be getting the collector resistance RC. And here we will be getting the RE emitter resistance. And this will be connected here. So here the current which is flowing is IE. And here the current which is flowing is IB. Okay. And next, in this RC, the current will be flowing is IC. Okay. And at this point, the voltage is VB or V of B. So if we apply KVL in this particular loop, we will be getting V of Thevenin is equals to R of Thevenin. We are representing this base voltage. Let's mention it here. We are representing this base voltage as Thevenin voltage, R of Thevenin. R of Thevenin into IB plus V of B, VBE plus IE into RE. And next we will replace this IE as IB plus IC. As we know, emitter current is equals to base current plus collector current. So then V of Thevenin, it will be equal to R of Thevenin IB plus VBE plus IB plus IC into R of E. Okay. So this is the value of V of Thevenin. And from this equation, we will find the value of IB. Okay. So here the value of IB is equals to V of Thevenin minus V of VBE. Okay. Minus IC of RE divided by R of Thevenin plus R of V. Okay. And if we find del of IB divided by del of IC, it will be equal to minus of RE divided by R of Thevenin plus RE. Okay. And if we apply this to this formula here, we will be getting stability factor as S equals to 1 plus beta divided by 1 plus beta RE divided by R Thevenin plus RE. So in this voltage divider bias, this stability factor, which is S, this has the minimum value for all these three biasing techniques. So for the fixed bias, the stability factor was maximum. So this stability of this particular biasing was very much low, as this was the least stable because the stability factor was highest. For collected to base biasing, the stability factor was at a moderate value. So it is moderately stable. And for this voltage divider bias, this stability factor has the least value. Okay. So this stability factor has the least value. So the stability of this voltage divider bias will be highest. As I have explained here, the minimum value is 1. Okay. My maximum value is 1 plus beta. If the stability factor tends to a maximum value, this will be least stable. And if the stability factor leads to a minimum value, then that's configuration will be more stable. So here for the phase bias, the stability factor was tending to, or it was equal to the maximum value. So the stability was least And in the voltage divider bias, the stability factor is tending to a least value. So, and we can also say it has the least stability, the voltage divider bias, it has the least stability factor among all of these three biasing mode. So this voltage divider bias has the highest stability among these three transistor biasing modes. Okay. So this is all for the transistor biasing modes. Thank you.